Okay, this is a video version of me going through the lecture material in a more serious manner. So today we are going to talk about these topics. So first, let me talk about the basic thing. So I assume you know all these. So what are these? For example, I assume you know what is a set. So this is a set. And I assume you know what this two symbol means. It means inclusion or membership. And I also assume you know what it is. It means complement. And we will use two bar to denote the number of elements in a set, or we call it cardinality. Okay, and we will always consider x is finite, meaning that x has finitely many numbers, so we do not consider infinite sets. So these are the basic assumptions. And then what's next? We are going to consider the following operation. You have already learned it in the set theory class. That is, the first thing is union. That means x or y. So this means the element x in x or x in y. Okay, and then we also have the intersection. That means and. That means both these are true. Okay, and we also have the complement, x minus y. This means x minus y. That means x, small x inside the big X, but it is not in y. Okay, so this is the basic operation. And now we also have an important product called Cartesian product, xy. Do not mix up Cartesian product with this. These two things are not the same thing. Okay, so for Cartesian product, it means the ordered pair small x small y such that x in x and y in y. Okay, and lastly, an important point is that we consider disjoint set. If x, y are disjoint, the definition is their intersection is empty set. And with this, then we will have the following funny thing: x or y, the number of elements will be just the sum. Okay, so we were going to talk about these three topics. So first, we talk about something called inclusion-exclusion principle. So what's that? So first, we need to recall this thing. So if two sets are disjoint, then their cardinality in the OR case is just sum. So suppose I want to consider A or B. I want to consider A or B. So now I'm going to do B as this thing, this blue bracket thing. So what is this? So A, so suppose this is A, and then suppose the green thing is B. Okay, suppose the green thing is B. B subtract A means everything in the red region. Everything in the red region is B subtract A. Okay, and you can see that A and this red region are disjoint. And therefore, A or B is the same as A or B minus A. Okay, and it's because they are disjoint, I can then call the blue equation here. These two sets are disjoint, so I can just say this is the first set and this is the second set, and therefore I have this and this. Okay, so I call this equation star. Okay, then what's next? I consider set B. Okay, for consider the set B, I'm now letting set B equal to B minus A or B and A. So what's that? So suppose this is my B. Okay, suppose this is my B, and then suppose I have a set A. Okay, this is my A. What is B minus A? B minus A is everything the red region. The red region is B minus A. What about B and A? B and A is everything the yellow region. You can see yellow region and the red region sum together give me the blue region. Therefore, this is the reason why I have the equal sign here. And then you can see red and the yellow region are disjoint, so I can call this again. I call the disjoint formula, I can write them like this, and I call this equation dagger. So now what I'm going to do is, with the star equation and with the dagger equation, I'm going to subtract them. So I'm going to subtract star dagger. So I'm going to subtract, okay? Subtract them. So I subtract them. So if I subtract them, this one will give me A or B subtract B, right? And then what's next? This side, okay, will give me A plus B subtract A minus the thing here, right? So it will minus B subtract A minus B and A, okay? And what's the funny thing? This term and this term are the same term. One is plus, one is minus, so they cancel out. If they cancel out, so I can just what? Ignore them. I ignore them. Then what's? I have this minus B here. I can move it to the other side. I move it to the other side, so I plus B, and this one gone. So what is this? This is A or B is A plus B minus A and B, which is the red box. So that's how you prove the red box. So now this is the case for two sets. What about three sets? I have three sets. A or B or C. So I'm going to do a trick. I just add a bracket here. Adding a bracket does not change anything, but the important here is this is three sets. Okay, now I add a bracket. It means I have only two sets. if I have two sets, it fulfills the case for the red box, so I can use the red box. So this is my A and this is my B in the red box. Then I just call the red box. I have what? The A itself, the B, which is the bracket here, this term, and the A and B, which is the A and B. Okay. Now for this guy, for the red term, I'm going to call the red box again and give me three things. So by doing this, I have expressed what? This term as this bunch of things. This thing I cannot simplify anymore. 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 This guy I can simplify. I can distribute the thing inside. Okay? So here's a rule about distribution. X and Y or Z is the same as X and Y or X and Z. So I use the blue thing. This guy become this. Okay? Now I have two sets. I can call the red box again. So this guy become here, this guy become here, and I have their intersection. And what's next? After I have this red thing, this guy I cannot simplify anymore. This guy I cannot simplify anymore. But this guy I can simplify. So this guy here, which is this term, I can remove the bracket and then I can move this guy to the other side because I can change the order. So I have this. A and A is just A. So I simplify it. And this guy I cannot simplify anymore. So it gives me this thing. So in conclusion, what I have is, for two sets, I have the formula 1. A or B is the same as A plus B minus A and B. For three sets, I have A or B or C is the same as A plus B plus C minus intersection of AB, intersection of AC, intersection of BC, and then plus the intersection of ABC. Okay? So what about four sets? I can do the following. So first, I take a bracket, and then what? Now there are two sets. I call the formula 1. Then I break it into this thing. And then what? This guy is this guy. Three sets. So I use formula 2 to break it into this thing. Okay? So now I have the equation like this. I need to simplify this guy again. Again, I'm going to distribute. I will distribute 3 times, so I have 3 terms. What is this? 3 sets, or I call formula 2 again. So I get this big chunk of thing. Now I get this big chunk of thing. What's next? There are many brackets here. I can simplify. For example, I can remove their bracket and then I move all the A to one side and then they cancel out. So in the end, I have this thing. Okay? So this is the idea. And notice that just it is important. Here I have a minus sign, but here I'm talking about plus. So if I want to put this thing into here, I need to be careful about the sign. So that's why here there's a plus, but here it becomes minus. Okay? But anyway, sign is not important. The idea is that how do you approach this by a recursion? That means using previous case. So now here's the grand summary. With nothing, empty set, 0 element. With one set, then this is just the formula. This is 2 sets, we have this inclusion-exclusion principle. 3 sets, we have this funny formula. 4 sets, oh, very complicated. And if I consider the number of terms here, for 4 sets, there are 4 single set terms. So there are 4 here. There are 2 sets, so double terms, but there are 6 of them. So 6. There are triple terms. I have 4. And quadruple term, 1. So I have this 4, 6, 4, 1. And for 3 sets, I have 3 single term, 3 double term, 1 triple term. So 3, 3, 1. I have these kind of funny numbers. And magically, if you consider multiplying polynomial, expanding this, and counting the coefficients, you get the same numbers. So in other words, doing this for exclusion-inclusion principle and also for multiplying polynomial, they have a bijection. Bijection meaning that they have a one-to-one correspondence. We will come back to this later when we talk about bijection.